Hey everyone, it's Benny, and today I'm going to be making an update to talk about my upcoming Advanced Redstone computer series. I'm going to talk a little bit about what you can expect to get out of it, what's going to go into it, when it's going to happen, and all that sort of stuff. And at the end, as a special bonus, I'm going to show you a little bit more of the ALU, talk a little bit about how it works, because I can see there was a lot of people who are interested in how I could possibly get something that was 5-tick ALU. And I might even show you a few more things I'm going to use in the computer. We'll see. But, to start off with, let's talk about the series. I'm going to start with when it's going to happen, because I'm sure there's a lot of people wondering, okay, you told us you're going to do it, when? When's it going to happen? And that is tightly interlinked with my current Ultimate Guide to Redstone series. Now, in that series, I've currently just finished the Logic Gate section, and I'm sure most of you already knew that, except maybe the obscure ones, because most of the people subscribed to my channel are relatively advanced in Redstone. Where I'm going to go from here in that series is I'm going to talk about circuits like latches, flip-flops, monostable circuits, and some more obscure ones as well. And I'm going to cover all that. And in addition, after that, I'm going to cover mathematical circuitry, addition, subtraction, possibly division. I'm going to talk about shifting, I'm going to talk about different ways of doing it, and after I cover mathematical circuitry, or at least close to finishing covering it, that's really where I want to be when I'm starting this series, because that's really what I want people to know when they go into this. And the big reason for that is because when I do this series, it's not going to be quite as much of a tutorial series anymore, because I'm going to go, or at least I'm hoping to go a lot deeper than that. I don't want to just show you, hey, place blocks like this, and you get computer. Ta-da! Which is kind of what I did with the Building a Minecraft computer series. I did talk a little bit about the explanation of why it was doing what it did, but I didn't really talk about anything else. I told you sort of why it worked. Didn't really show you why the Redstone devices worked all that much, except a little bit of the adder. Didn't really talk about the math of why the design worked, or why that was a halfway decent design, or why the design could work like it did. And those are all things I really hope to cover in the more advanced series. And in part, that's to sort of replace the Designing a Minecraft computer series, because like I said in that series, if I continue doing the Designing a Minecraft computer series as I was doing it, it would work extremely effectively, but by the end of it, it would take the rest of my lifetime to finish, so I'm hoping that if I cover all the math behind it, and which we'll talk about the math of what makes a good design, and why does certain designs can have certain advantages, and why a bigger and slower design can actually be better than a smaller and faster design in just about every case you can imagine, and how you can find which of those designs are better. So, which I know is a little bit weird. I actually did a little bit of that in the ALU, and that's how it's 5 ticks, because making something that's 5 ticks that does as much functionality as my ALU, technically impossible in the current implementation of Redstone. So I'm hoping to talk to you a little bit about how I can make it 5 ticks, even though it's technically impossible. But anyways, so yeah, hopefully that gives you a little bit of better idea of what I'm planning on doing in the Advanced Redstone series. And, just one thing I want to bring up while I'm on the topic. In the Ultimate Guide to Redstone, when I'm doing the mathematical section, when I'm talking about adders, one thing I'm hoping to cover is the carry look-ahead adder, which, if you don't know, is generally accepted by a very large portion of mathematicians and scientists as the fastest adder design in existence. So I think a couple people might be interested in that, so just thought I'd mention that. But yeah, so a couple more things about the Advanced Redstone series. Advanced Redstone computer, that is. One thing that you might be interested in is I'm not just going to have one processor this time. I'm actually going to have 2 processors. A central processor, a CPU, like every computer has, and I'm also going to have a separate graphical processor. So, and it's not going to be like my other GPU, which essentially has fill commands and a screen. I'm hoping to do a more complete graphical processor, which hopefully includes basic fill commands and a screen, but also has a few more things, including dedicated video memory, and dedicated graphical processing commands. So hopefully that will be a little bit interesting. And I'm also going to talk about how all that can interact, like with the program command system and the processor and the graphical processor. I'm going to talk about how all those can interact. And I'm also going to talk about synchronization a lot, because I haven't really talked about that, but it's pretty important if you want decent performing Minecraft computers, or any computer really. And the big issue there is the central processor and the graphical processor are going to run on two different clocks. The graphical processor is going to have a much slower clock than the central processor. And I'm going to talk about how we can get those components to work together even though they're on two different clock rates. Namely, the graphical processor is going to be a lot slower than the central processor. So yeah. And just to give you an idea of what features I'm going to have in the graphical processor, right now I'm definitely going to have box rendering, just like I had the other one, so hollow boxes or filled boxes. Boxes. And I'm considering implementing line rendering. It's going to be incredibly slow, but if I implement line rendering, you'll be able to make a lot of different graphical shapes. So, yeah. And other than that, I really think that's everything I want to talk about as far as what you can expect to get from the series. Other than, it's going to be one really big and really long series when I start getting into it. And yeah. So, with all that out of the way, now I'm going to talk to you about some of the components that are going to go into the computer. Starting with the ALU and a little bit more information about how it works. So, this is the ALU. This is ALU like you saw before. But I've made a couple changes to it. As you can see, it's now a lot bigger. Same speed, but it's a lot bigger. Here's what I changed. First off, this section right here, if you remember, before this went up a couple more blocks. I actually compacted this a little, and now it's a lot smaller. Same speed, just a lot smaller. And the big addition to it is the conditional unit, right here. It doesn't add any delay at all, so that's a pretty cool thing about it. But it does enable the ALU to get greater than, less than, or equal to. As you can see right now, I have A is equal to B, A is greater, and B is greater. And since I have 0 and 0 in the ALU right now, it's A is greater. Now, I already showed you how the ALU worked in the last video. In this video, I'm going to get a little bit more technical on it. I'm going to tell you a little bit more of the details of how it works, what makes it tick, and hopefully, after that, maybe you won't be able to build it, but hopefully you'll at least understand that I'm not doing some magical wizardry to get this thing to work. Hopefully you understand there is a method to the madness. It's just standard redstone used in a really interesting way. But first off, I'm going to just complete the demonstration, because last time I never really got to demonstrate just how incredibly fast this thing is. In this video, I want to give you a little bit of a demonstration, because now I added registers to it. Now the registers technically aren't part of the ALU, but what they will let me do is they will let me trigger an input from the other end all the way over there. So you'll be able to see just how quick a signal passes through this ALU. So first off, I'm going to pick two numbers. The top number I want 101, so that's 128, that's 64. Plus 32 is 96. Plus 4 is 100. Plus 1 is 101. And just to double check, because I don't want to input the wrong number, 64 plus 32, that's 96. Plus 4, 100, 101. Okay. And for my second number, I'll put in 55. So 50 starts at 32. Okay. Plus 16, that is 50 plus 16 is 48, I'm pretty sure. Yes, okay. Now, I want to add 8, I think. Plus 48 plus 8 is 56. Okay, that's actually too much. So, plus 4. Okay, so that right there should be 51. I'm pretty sure. Not 51, 55. Okay, so that's 101 plus 55. I'm going to go ahead and save input B as an input. And what I'm going to do is I'm going to trigger input A when I'm done. So to start off with, I'm just going to add it. And I'm going to flip this lever. And keep in mind, registers are not instant. It takes 2 ticks to save something to the register. So this should take, in theory, a maximum of 7 ticks. So you ready? 3, 2, 1, go. Done. That fast. I told you, it's a pretty fast AOU. So yeah, there. Now all the math is done, and there's the answer. And just to demonstrate that it's consistent, because I only did addition, and addition should, in theory, be pretty fast, I'm also going to demonstrate doing a little bit more. First off, I'm going to do subtraction using 2's complement. And I'm also going to divide it by 2. So now, let's hit the button. 3, 2, 1. Wait, before I do it, remember, this is not only subtracting it, it's subtracting 101 minus 55 and then dividing that by 2. Ready, set, go. Done. It's pretty fast, yeah. And yeah, so there you go. That's the final demonstration I'm going to give. The rest of this video, or the rest of this part of the video, I'm just going to be a little bit technical about what this thing can do. So first off, I'm going to just... why not? I can keep it saved. So first off, I'm going to just undo everything. Now it should be back in default state. Okay. So, there's a couple things I changed here. First off, like I said, there's all that. But there's a couple more features it has. In the previous version, I could only do subtraction with 2's complement, which is inverting input B, and then adding 1. In this version, I can also do subtraction with 1's complement, which is inverting input A, and then inverting the output. That didn't work in the previous version, so, yeah. Now it's working, yeah, okay. I thought for a second there it screwed up, but then I realized I was adding something that added over 128, so 128 actually is correct in this case. But anyways, yeah. So that's one big feature. Now the other thing I want to talk about is how on earth... Actually, well, before I do that, I wanted to demonstrate the conditional unit. I almost completely forgot about that. So right now, A is greater, because I have 101. So A is greater. If I added an extra 1 to... So 128 to B. Now B is greater. And of course, you already saw if they were exactly the same, that came out correctly as well. So, how can I get the conditional unit to not affect the speed of the AOU? Simple. The conditional unit's actually completely separate from the rest of the AOU. What I'm doing is I'm just plugging input A into the conditional unit right here, and then it's going into the rest of the AOU, and input B is going into the conditional unit right here, and then there it's going into the rest of the AOU, and that adds no delay at all. Because, yeah, and since the conditional unit itself is 5 ticks, adds no delay at all to the AOU. So that's how I did that. And now I've covered all that, I can finally talk to you a little bit about how I got this thing to work in 5 ticks. So, as I explained in the Designing Minecraft Computer, the way you can judge how fast a Redstone device is through signal flow. Whatever the slowest speed a signal can pass through something, that's how fast it is, because that's the slowest speed something can pass through it. So, let's look at the signal flow. First off, it goes over the conditional unit, and we already concluded that's 5 ticks, so we can completely bypass that. Now, next, it goes straight into the adder. That's somewhere in... Actually, no, not the adder. It goes into invert input A and invert input B. Those are done with XOR gates, and that's 1 tick. So that's where the first tick of delay is, right here. Either with this repeater, or with this torch. That's the first tick of delay. So next it goes into the adder, which is somewhere in this general mesh of redstone. And this is an XNOR based redstone adder. It's instant carry. And it's 3.5 ticks. Although in this implementation I can use it as a 3-tick adder, and I'll explain why that is in a moment, but it's technically a 3.5 tick instant carry. I'm pretty sure this is the fastest adder design possible, but at least in Minecraft that is, but you know, It's the one I'm using. If there's something faster, maybe I'll try seeing if I can get someone to work with that. But yeah. So, that's somewhere in this general area. This is the carry-in. And that's our command, I'll explain. And yeah, then after passing through the adder, so it's 1 tick and then 3 ticks. So there's 4 ticks at this point. It goes into the right shifting unit, which is what I use for division. That's 0 ticks actually. The right shifter is instant. So it's still 4 ticks after here. And then finally I have an invert output option. That's 1 tick, and that's how it's 5 ticks. That's the signal flow through the ALU. So now I mentioned that even though the adder is 3.5 ticks, I can use it as if it's a 3-tick adder. So how is that possible? It's actually done with a little bit of a hack. So first off, the reason it's 3.5 ticks in the first place is because pistons sometimes add a half tick of delay. Some instances of pistons are 1/2 tick. But in this case, I've actually managed a way to hack around that because I've discovered only certain input combinations will cause that half tick to actually amount to anything, because Redstone doesn't work on half ticks. You can only have full ticks, and that's it. So it can either be 1 tick or 2 ticks. I discovered it only creates 2 ticks in the few rare input situations. So what I did is I created a hack component, which is right here, which actually involves a second carry wire. And it's a little bit weird, I know, but what that'll do is that'll essentially divide the inputs. Any input that would normally not create the extra tick of delay, that'll pass through as normal. That'll be a 5 tick. Anything that would trigger it is normalized so that it will always take 7 ticks. I know there should be alarm bells going off your head like, okay. If a signal can pass through in 7 ticks, how can this possibly be a 5-tick ALU? It's actually done with a really clever bit of Redstone trickery. So, here's how it works. First off, the important thing here is that the extra ticks are in the adder, not in the ALU itself. So, the adder is 3 ticks for most cases, and 5 ticks for other cases. That's the first important thing. The second important thing to note is that when you're getting that extra half tick of delay, you already have the answer. It's just the answer isn't, I guess you could say, normalized, isn't stabilized. It could still potentially cause extra ticks of delay somewhere down the line. It takes 7 ticks to normalize the input so that it's completely stable and will never cause any extra ticks. But in 5 ticks, you will still have the correct answer. That's the really important thing here. So, that's why it can be 5 ticks. All I have to do is I have to make sure that when I hook this thing up, anything that requires a normalized signal is at least 2 ticks closer than anything that doesn't require a normalized signal. And that will ensure that I can use this as if it's a 5-tick adder, even though 5-tick adders are technically impossible in Minecraft. So yeah. So that's a little bit of the trickery of how I did that. And I never really went over the features of how what this thing does, so I guess I'll go over that really quick. This right here, what this does is it disables the carry. That's what allows me to do it as an XOR gate. This right here, this will actually alter the input scheme of the adder. I'll go a little bit more in depth on this particular command when I do the actual series, but what this does is it'll alter the truth table of an XOR gate, and it will make it so that in one case it will get a 1 where it wouldn't normally get a 1. And if I use that in combination with input A and input B, and input output, invert, not input, that will let me use the adder as if it's a logic gate. And it can be used as if it's any logic gate I can imagine. So, yeah, pretty interesting feature right there. And again, I'll talk a little bit more about that because I'm concerned that it'll take too long if I explain it right here. But I'll explain that in the series, don't worry. And really, I think that's all I would really want to cover for this. This is all I want to talk about for the ALU. Again, you'll get a little bit more in-depth explanation of how it works in the series. In fact, you'll get a much more in-depth explanation. One thing I'm going to talk about just here really quick is when I'm doing the series, I'm not just going to explain how this thing works. I'm going to explain the math behind it. And I'm going to do that in the form of big O notation, which is what computer scientists use to measure how fast a certain process will be completed. So, I'll be talking about how this thing works and how the whole computer works in terms of big O notation. So I'm going to teach you that and how all that works. And using that, we'll be able to determine everything we'll ever need to know about this ALU in the computer in terms of performance. And that's how, even though this ALU is bigger and slower than other designs, it can still be used as if it's faster than any other design out there that I've at least found. So yeah. But that's all I want to talk about the ALU. And while I'm here, I guess I'll show you a few more things. So, one moment. Okay, here's another component. This is the memory system I'm planning on using for RAM. Incredibly compact memory cell. It's this right here, 8 bytes of memory. Ridiculously compact. Each individual memory cell is 2 by 2 by 13. And it's also faster than the other memory cell I showed. So yeah, incredibly compact. One thing I really want to point out though, not my design. This design is done by Titanic Nut. And I'm really going to try emphasizing that a little bit more when I use something that's not my design, because the last time I did that, I believe, was in the GPU series, in the Phil X and Phil Y system. I thought I had made it pretty clear that it was Lawrence Wayne's design, not mine, but some people apparently didn't get the message, because I saw on some RDF applications, some people had mentioned that GPU Phil X and Phil Y system was my design. No, guys, that's Lawrence Wayne's design. Give the man some credit. He actually does some good things with Redstone, believe it or not. I'm not the only person who invents Redstone devices. So yeah, this design, Titanic Nut, GPU Phil X Phil Y system, done by Lawrence Wayne. Don't get those confused. Those aren't my designs. Anyways, with that out of the way, let's talk a little bit about this. So like I said, incredibly compact, 52 blocks volumetrically. I'm not convinced it's the smallest design possible. I'm convinced there's a way to get this 1 block smaller, but since it's 1 block vertically, and I really don't care about vertical blocks, I'm not going to bother, but I'm convinced there's a way to make it smaller. So, if anyone wants to try and find that, I'd be very interested, because I'm convinced it's possible. But anyways, so just to demonstrate it working, I'm going to save some things to memory. So what should I save? I'll just save this. There's the lines. Incredibly fast. It's 2 tick write and 1 tick read. So if I read, there. Incredibly fast. The read and write delays do compound, however. In my design, which was 3 by 2 by 13, the delays, they were 3 ticks each, but they did not compound. These do compound, so yeah. Just thought that would be worth mentioning. Now, and again, also, since it is saving, I can still read the data, even though I don't have it anymore. I can write something else to memory, like, I don't know, this. Why not? Let's write. Just keep writing, I don't know. Let's write something like this. Oh, did I already save something here? Yes, I did. And that's all I have the patience to save to, but for just demonstration purposes. So yeah, now if I read this one, you'll see I'm getting that. Now I'm getting that one. And now if I read this one, I'm getting that. So yeah, incredibly compact, incredibly fast. Absolutely love this design. Thank you, Titanic Nut. Absolutely love it. So that's the memory cell. That's really as far as I want to go here. Other than, yeah, no, I'll leave that for a surprise in the series. So yeah, that's the memory cell. And I have time, I'll show you one more thing. Okay, here's the next component. And this is not part of the central processor. This is part of the graphical processor. And it's actually 2 parts in one, so you get sort of a bonus. This right here, what you see in front of me, is what I'm planning on using for the screen in my graphical processor. So, you get a bit of a bonus. The reason I'm using this design rather than, it's not in render distance, but rather than the type of screen I used in my other GPU series, is because that type of a design really doesn't leave much room for features. It's good for a screen, it's good for displaying lots of pixels in a small space. Doesn't leave much room for a lot of features. And in addition, it also if you're trying to like play a game on or something on it, it's easier just to hit the button and look down and see what's happening than hit the button, rather than just hit the button, turn around, turn back. You know, it's easier that way. So yeah, and that's the reason I'm going with this design. I also did a bit of interesting redstone design here. There actually is a pretty good reason for the way I did the screen this way. The reason I did the redstone design like this is because it's artistic right here. I thought it would be more interesting than just having a straight up grid like this. I thought that would be a little bit more boring. So that's why I'm doing it like this. Also, there's multiple ways of looking at it. You can look at it like it's 4 squares around a ship. You can look at it like these are parts of a saw blade. You can look at it like it's a net. You can look at it like all sorts of different things. So that makes it good for games since you can see the pixels in different ways. And the reason I did the repeaters like this is because it has to do with your brain. One of the most powerful visual features of your brain is edge detection. If I just did this flat redstone on black wool, the image would be really hard to see. But if you put repeaters around the edges like this, that will create a difference in the edge and not strictly the image itself. As your brain is really good at seeing edge detection, it dramatically increases the visibility. So that's the reason for repeaters. The reason for glowstone: looks cool and keeps mobs away. That's about it. So yeah, that's all I have to say about the screen. Now let's talk about the other component. The other component is right under the screen. This is not the full graphical processor. This is a very, very small part of it. This is a box renderer. More specifically, it's a hollow box renderer, because in my other GPU, if you wanted to do a hollow box render, you would have to do this weird stuff where you'd have to do 2 cycles where you'd fill like this, fill like that. And it also was not compatible with other images. It would erase anything else you had on the screen, so not the greatest design. So I've created a dedicated hollow box renderer, which has none of those problems. And I like this a lot better. This is done with proper English 19's hollow box rendering algorithm. I absolutely love that algorithm. It's pretty fast. It's really cool looking when it renders a box, and yeah. I can't guarantee this will be the final box renderer I use because I haven't asked his permission to use it yet. And I'm not a big fan of using people's stuff without their permission, so I'm going to ask his permission at some point. And if he agrees, this will be the final hollow box renderer I use. But yeah, it's not his design, it's just his algorithm. The renderer itself is my own design. It's designed specifically to work with the graphical processor that I'm going to be using. But yeah. So here's how it works. Essentially, you have a whole bunch of cells, and underneath each cell you have a lever. And of course, if you select a lever, that will select that cell as one of the corners of the box. So if I flip that lever and I go up, you'll see the processor has now, or the renderer, has selected this giant sort of crosshair around the cell I've selected. And if I select another cell, say, I'll go under, I'll select this one right here. Select that one. What it'll do is it'll connect the cells, and now I have a box. Granted, not the most interesting box, there's no space in between, but yeah. And if I want to clear it, what I have to do, first off I have to uncheck the boxes, because once you actually render the box, it actually saves it for you. So now if I go back above, even though I turned off the rendering, the box is saved, and I can keep using it. That's one thing I really like about that design. And if I want to erase it, what I have to do is I have to go to one of the cells, and I have to hit the erase command. And you'll hear a bunch of pistons trigger, and now it's erased. So now, if I go up, it's clear. Now it doesn't give you a really good idea of how it looks or how fast it is, and you're really not going to get a good idea of how fast it is just because of the way Minecraft renders things as large as this, but I did go ahead and pre-connect some wires to some of the cells to hopefully give you a little bit better idea of how it's actually rendering. So I'm going to select that cell right there. As you can see, selected it. Not the best idea of how fast it is because of the way Minecraft renders the chunks. And this one selects that cell right there. Again, Minecraft renders the chunks a little bit weird. So now let's look at it actually drawing the box from those 2 points. And there. Now it's drawn the box. And again, the algorithm is proper English 19's design. I did not invent this method of generating boxes. I just designed the cell. He had his own design, but I decided not to use it because I didn't think it would be the best design for my overall graphical processor. But this is his algorithm, so don't give me credit for the algorithm. That's his algorithm. And here's a clear command, so you can see it clearing. And the clear command right now is actually a little bit of a hack. The real clear command is going to be a little bit different, a little bit faster, but yeah. So that's hopefully a little bit of an idea of how the whole thing works. It's pretty compact for what it is. It's not the most compact. I know quite a few ways I can make this smaller, but there's a reason I made it as big as I did. It's 8 by 8 by 13. I know for a fact I can make it a lot smaller than that, but I chose not to, partially in favor of speed, partially in favor of just the way I wanted it to work. And yeah, this is one individual cell, so you can look at it. And there you go. So, that's all I really want to show off, because I think if I show off any more than this, I'm going to give away a little bit too much. But yeah, hope you enjoyed. And I'll see you in the Advanced Redstone Computer Series, which should be coming up. I'll take a stab in the dark and say within the next 15 videos of the Ultimate Guide to Redstone. Of course, now that I said that, that's going to be horrendously wrong, but yeah. Hope you enjoyed, hope you learned, and see you next time.